for more than 15 years, working in a high-specialty workshop. There, I learned an uncomfortable truth that manufacturers hide behind simplistic user manuals. Your car is designed to be politically correct, not to be efficient. Brands program computers so that the vehicle behaves in an anesthetized way, prioritizing excessive smoothness that ends up numbing the mechanics. I have seen hundreds of customers spend thousands of dollars on new parts when the only thing their car needed was an electronic release. What you are going to read next are not simple maintenance tips. They are the secrets of grey engineering, tricks that dealerships label as illegal because they eliminate the need for their technical services. We are going to enter the digital guts of your vehicle to wake up the engine you actually bought, but that the factory decided to limit. The adaptive transmission reset. The majority of drivers of modern automatic vehicles notice that with the passing of the months, the car begins to feel heavy. The gear changes become slow, and the response when stepping on the accelerator is lazy. This is not a mechanical failure. It is an excess of artificial intelligence. The Transmission Control Unit, or TCU, has an adaptive memory that learns your habits. If you drive for a long time in traffic jams or in a very conservative way, the gearbox learns to be slow to save fuel and be smooth. Basically, you have educated your transmission to be boring. The trick to reverse this is to perform a purge of the adaptive memory without tools. In most cars with an electronic accelerator, the process is almost cinematic. You put the ignition in the on position without starting the engine. You step on the accelerator pedal to the floor for exactly 30 seconds. Then you turn off the ignition without releasing the pedal, and finally you wait 2 minutes in total silence outside the vehicle. During those 120 seconds, the solenoids of the box recalibrate to their factory values. Upon starting, you will notice that the transmission becomes aggressive, fast, and decisive again. It is as if you had removed a backpack of 100 kilograms from the car. The response is immediate because you have erased months of digital laziness habits. The Transmission Control Unit, known as TCU, is an electronic brain that not only executes gear changes, but acts as a psychologist of your driving. Through a process called fuzzy logic, the computer analyzes the speed with which you press the pedal, the lateral G-force in the curves, and the frequency of the braking. If you have spent months driving in a congested urban environment, the TCU reduces the pressure of the hydraulic solenoids so that the changes are almost imperceptible, which in turn generates a massive delay or lag when you need immediate power. The 30-second trick to reset this volatile memory is, in essence, a purge of the adaptation files. Throttle Position Sensor Calibration with Multimeter. The Throttle Position Sensor, or TPS, is in charge of translating the movement of your foot into an electrical signal for the computer. Over time, due to engine heat, this sensor suffers a degradation in its internal resistance. Manufacturers say it is a sealed part that must be replaced, but we tuners know that an adjustment of barely 1 millimeter can change everything. If you feel a delay or lag when you step on the pedal, it is very likely that your TPS is sending a voltage signal out of range. For this precision trick, you need a digital multimeter. You must measure the voltage on the signal wire with the ignition on. Most engines require exactly 0.5 volts with the throttle closed. If your multimeter reads 0.4, the car will feel lacking in initial power. If it reads 0.6, the idle will be unstable. By loosening the sensor mounting screws and rotating it minimally until hitting 0.5 volts, you eliminate the computer reading error. The result is a perfect physical and electrical connection. As soon as you touch the pedal, the engine reacts with a sharpness that no new dealership part would give you without this fine adjustment. The throttle position sensor is a precision potentiometer that must inform the ECU about the exact angle of the throttle with a margin of error that is almost zero. However, the accumulation of extreme heat in the engine bay causes the internal resistance of the sensor to vary, shifting the reference voltage signal. If the sensor sends, for example, 0.3 volts instead of the 0.5 required at idle, the computer interprets that the pedal has not yet been touched, generating that annoying initial vacuum when trying to start. Performing the manual adjustment with a multimeter is a task of microengineering. By loosening the mounting screws and rotating the sensor body just a fraction of a millimeter, we are physically recalibrating the internal carbon track, bypass of the idle memory via terminals. It is very common that after cleaning the throttle body to improve performance, the car is left with the revolutions per minute oscillating or too high. This happens because the computer has a RAM memory where it saves the adjustments it made when the system was dirty. The dealership will charge you a fortune for an idle relearn, but you can force it yourself through a total discharge of capacitors. You disconnect both terminals of the battery and, with a jumper cable, join the car cables, never the battery terminals, for 15 minutes. This procedure drains all residual energy from the engine control unit, erasing volatile learning data. The alternator voltage hack. This trick is among the most advanced and requires understanding that a car does not run on 12 volts, but ideally on 14.4. Manufacturers limit the voltage to minimally prolong the life of halogen bulbs, but at the cost of a weaker spark plug spark. A weak spark means incomplete combustion and less power. Automotive electricity experts insert a low-drop diode in the detection or sense wire of the alternator. By doing this, you trick the alternator regulator into believing that the battery voltage is 0.5 volts lower than it actually is. The alternator compensates by raising the output to 14.2 or 14.4 constant volts. This increase in electrical energy causes the ignition coils to saturate faster and generate a much more powerful spark. The engine feels more elastic, the lights are brighter, and the thermal efficiency improves because you are burning the fuel in a more violent and complete way. It is an invisible performance improvement that takes advantage of the energy reserve that the alternator always has available, but that the stock electronics decide not to use. Most modern automotive electrical systems are designed to operate in a state of efficiency survival, where the alternator barely delivers 13.5 volts to reduce the mechanical stress on the engine. However, an internal combustion engine is, in essence, a machine that depends on the speed of propagation of a flame. By applying the diode trick to the reference wire, we force the regulator to raise the output voltage to 14.4 volts. This difference of almost 1 volt seems insignificant, but in the world of ignition physics, it is a quantum leap. The ignition coils, upon receiving a higher voltage, can saturate faster and generate a much hotter and more stable electric arc at the spark plug electrode. Activation of the hidden engineering menu. The dashboard of your car is a simplified user interface so that you do not worry. For example, the temperature needle is programmed to stay still in the middle, even though the engine is at 80 or at 100 degrees. For the manufacturer, if it does not move, the customer does not call. But for an enthusiast, that lack of precision is dangerous. Almost all modern cars have a hidden engineering menu accessible through combinations of buttons on the steering wheel or the radio. By activating this mode, the digital screen will show you the exact temperature of the coolant in degrees Celsius, the real pressure of the oil pump and the voltage of the system in real time. In the workshop, we use these menus to detect thermostats that are starting to fail long before the conventional needle gives the alarm. Having access to these data allows you to anticipate catastrophic breakdowns and know the real state of health of your mechanics, breaking the barrier of chewed information that the brands impose on us. The conventional instrument panel is, for engineers, a comfort interface. The needles are programmed with smoothing algorithms so that the driver is not alarmed by the natural fluctuations of thermodynamics. For example, while your temperature needle marks 90 fixed degrees, the engine could be oscillating dangerously between 95 and 105 degrees. By activating the hidden engineering menu, you unlock direct access to the vehicle data bus. This allows you to monitor the raw data flow, such as the oil temperature in real time, which takes much longer to heat up than the coolant, or the turbo boost pressure in millibars. Unlocking of the programmable central locking. Did you know that your car probably already has the ability to close the doors automatically when exceeding 20 kilometers per hour, or to unlock only the driver's door for safety? But those functions are deactivated from the factory. Dealerships usually charge for programming these features as if they were a luxury extra, when in reality they are just lines of code already present in the body module. In most vehicles, there is a sequence with the central locking button and the key. For example, holding down the lock button for 5 seconds with the ignition on will activate the automatic locking by speed. These configuration tricks are documented in technical workshop manuals but omitted from the owner's manual. Unlocking these functions improves your daily safety and the comfort of the vehicle without the need to go through the checkout or install external modules that could compromise the original electrical installation. This is one of the best-kept secrets by after-sales departments who usually charge for activating convenience packages that are already physically installed in the car. The Body Control Module, or BCM, is a versatile computer that manages everything from the lights to the door locks. Through specific sequences of presses on the remote and turns of the key, you can program functions such as the automatic locking of locks upon reaching 20 km/h or selective opening, which only unlocks the driver's door to prevent strangers from getting into the car at a traffic light. The logic behind hiding these functions is purely commercial, but from the point of view of user engineering, they are essential. The intake temperature sensor trick. The car computer calculates how much fuel to inject based, among other factors, on the temperature of the air entering the engine. Cold air is denser and allows more power. The power resistor trick consists of deceiving the ECU through a small modification in the intake air temperature sensor known as IAT. By placing a specific resistor in series with the sensor, the computer believes that the outside air is about 10 or 15 degrees colder than it actually is. In response, the control unit slightly enriches the mixture and advances the ignition timing. This translates into an immediate gain in torque, especially in accelerations from low revolutions. It is a classic trick of the enthusiasts of the 90s that continues to work in many current engines, allowing the engine to breathe and feed as if it were always on a cold winter morning, even in the middle of summer. Air density is the limiting factor in the production of engine torque. The engine control unit, or ECU, adjusts the injection time based on the temperature of the entering air. Cold air is dense and requires more fuel to maintain the ideal stoichiometric ratio. The trick of the resistor inserted in the IAT sensor is a physical manipulation of the mapping table. By shifting the resistance signal, we indicate to the computer that the air is about 10 degrees colder than real. As a consequence, the ECU enriches the mixture and, most importantly, advances the ignition timing several degrees. Manual synchronization of keys with transponder. Losing a key or having the remote control deprogram is one of the most lucrative situations for agencies, which charge hundreds of dollars for a synchronization process that often takes 10 seconds. However, if you already have a key that works, most systems allow you to program a second or third key through a manual sequence. The process usually involves putting the original key in the ignition, turning to on 5 times, and then inserting the new key and pressing the lock button. This auto-learning protocol is designed for situations where the customer loses the key far from an agency. Knowing the specific sequence for your model saves you the cost of professional programming and gives you the independence to keep your access systems always operational without depending on the schedule of an official workshop. The immobilizer system is one of the largest sources of income for dealerships based on the user's fear of being blocked. However, most automotive security protocols include a manual learning mode designed for emergency situations in remote areas. This process uses the master transponder logic to authorize new digital signatures. By performing the on and off sequence in intervals of 10 seconds with a key already programmed, you open a programming window in the EEPROM memory of the immobilizer. If you introduce a blank key at that moment, the system clones the digital identity of the chip instantaneously. Handbrake adjustment from the drum. The most common error is to adjust the handbrake by tightening the nut that is under the center lever. Doing this only stretches the cables and leaves the main brake pedal with a spongy feel. The real and professional adjustment is made directly on the rear wheels, manipulating the star mechanism that expands the shoes. By lifting the car and manually adjusting this star until the shoes barely touch the drum, you achieve 2 things: a handbrake that locks with only 3 clicks, and, most importantly, a brake pedal that reacts much higher up and with more firmness. By eliminating the dead play in the rear part, you improve the distribution of braking and the total safety of the vehicle. It is a mechanical precision adjustment that transforms the sense of control of the car, and that is rarely done correctly in quick maintenance. The majority of drivers believe that the handbrake is an independent system, but in reality it is the heart of the balance of the rear braking. Adjusting the cable from the center lever is a patch that only stretches the steel and leaves the brake shoes too far from the drum or the disc. The professional adjustment is performed through the ratchet or star mechanism hidden in the axle. By expanding the shoes manually until the friction with the friction surface is minimal but existing, we reduce the hydraulic travel necessary for the pistons to act. This has an amazing side effect. The brake pedal feels much firmer and the front braking becomes more efficient, since the rear system begins to bite milliseconds before, preventing the nose of the car from sinking excessively. Dive effect. It is a braking geometry adjustment that improves stability in emergency braking and guarantees that the handbrake locks the vehicle with minimal effort, maintaining the correct tension in the cables and avoiding premature wear of the drive components. the thermal decarbonization by water injection. This is perhaps the best-kept secret by engine rectifiers. During the Second World War, aviation engineers discovered that injecting a fine mist of water into fighter engines not only cooled the combustion, allowing more power, but left the cylinders impeccable. Currently, engines accumulate a carbon crust on the piston heads and in the combustion chambers due to poor fuel quality and urban driving. That carbon generates hotspots that cause detonation, a phenomenon that destroys the rings and connecting rods. The trick, which must be executed with millimetric precision, consists of introducing distilled water through a vacuum intake of the intake manifold, while the engine is at its operating temperature and maintained at about 2,500 revolutions per minute. Upon coming into contact with the scorching heat of the combustion chamber, the water instantly turns into overheated steam. This massive expansion and the thermal shock detach the hardened carbon as if it were paper, expelling it through the exhaust in the form of fine soot. It is an internal pressure wash that returns the original compression to the engine. Manufacturers prohibit this trick because, if done wrong, introducing too much water at once, a hydraulic shock occurs that bends the connecting rods. But done correctly, it is the cheapest and most effective way to rejuvenate an engine block. This procedure is a master lesson in thermodynamics applied to internal cleaning. The carbon that accumulates on the valves and on the piston crown is nothing more than poorly burned hydrocarbons that have solidified. Chemical solvents are often not strong enough to dissolve these hardened crusts, but water has a unique property: massive volumetric expansion, the oxygen sensor deceiver with spacer. We reach a terrain that environmental authorities detest. When a catalytic converter reaches the end of its useful life, the car computer detects that the exhaust gases are no longer being cleaned correctly and turns on the fault light, putting the engine into a protection mode that reduces power and increases consumption. Changing an original catalyst can cost more than $1,500, an expense that many times does not make sense in a vehicle with 10 years of use. The grey engineering trick consists of installing an oxygen sensor spacer, also known as a mini catalyst. It is a piece of bronze or steel that is screwed between the exhaust and the second oxygen sensor. This spacer moves the tip of the sensor away from the direct flow of the gases, making the reading much more stable and clean. The computer, upon receiving this filtered signal, believes that the catalyst still works perfectly and allows the engine to operate with its maximum power maps. It is a physical hack that eliminates the emergency mode and allows you to continue driving with optimal performance without having to mortgage your house for an emissions part. When a catalyst begins to degrade, the computer enters a mixture correction loop that often results in an engine that feels choked. The secondary oxygen sensor is a watchdog that, upon detecting an erratic reading, orders the ECU to delay the ignition timing to try to protect the environment, even if that means destroying the efficiency of the engine. The physical spacer acts as a mechanical low-pass filter. By moving the sensor away from the main flow of hot gases, we reduce the frequency of the signal that reaches the computer. The ECU interprets this stable signal as a catalyst functioning in optimal conditions, which allows it to exit the safety mode and return to using the high-performance injection maps. The transmission oil trick in diesel. Modern diesel engines are extremely sensitive to the lack of fuel lubrication. Current diesel, known as ultra-low sulfur, is much drier than that of 20 years ago. This causes high-pressure pumps and injectors to suffer friction wear that generates metallic microparticles, which end up destroying the entire fuel system. Veteran truckers who manage to get their engines to exceed 1 million kilometers have an illegal trick in the eyes of particle filter regulations: adding a small dose of automatic transmission oil, ATF, or two-stroke oil to the fuel tank. The proportion is usually 250 milliliters for every 60 liters of diesel. These oils are designed to burn without leaving carbon residues and possess superior lubrication capacity. By mixing with the diesel, they coat the moving parts of the injection pump with a protective film, reducing metallic noise and extending the life of the injectors spectacularly. It is a life insurance for your diesel engine in a world of dry and poor fuels. In diesel engine engineering, the lubrication of the high-pressure pump depends entirely on the fuel. Modern diesel, being desulfurized, loses much of its lubricating viscosity, which generates erosion wear in piezoelectric injectors. Automatic transmission oil, or ATF, is a hydraulic fluid with extremely high shear resistance and extreme detergent properties. By adding a small proportion to the fuel, we raise the lubricity of the diesel above the minimum factory standards. This oil coats the walls of the pump and the seats of the injectors, reducing metallic friction and the heat generated by injection pressures that exceed 2000 bars. Restoration of headlights by steam polymerization. If you have tried polishing your headlights with conventional creams or sandpaper, you will have noticed that in 3 months they are yellow again. This happens because the polycarbonate of the headlight is left exposed without protection against ultraviolet rays. The definitive method, considered illegal in some safety manuals due to the toxicity of its components, is the chemical polymer vapor system. After a deep sanding that removes all surface oxidation, a thermal cup is used that vaporizes a special liquid polymer, based on acetone and other sealing compounds. When passing the vapor over the headlight, the plastic melts at a microscopic level and is instantly sealed with a transparent and ultra-hard layer. Unlike spray varnish, this polymer integrates into the structure of the headlight, returning a clarity of 100% and a protection that lasts years. It is the only way to recover the light safety of an old car without buying new optics that cost a fortune. The problem with conventional polishing methods is that they leave the polycarbonate porous and vulnerable. This trick, illegal for its handling of industrial chemicals, uses high-purity acetone vapor mixed with liquid polymers. By heating the mixture to exactly 56 degrees Celsius, the resulting vapor has the capacity to melt the surface layer of the headlight at a microscopic level, eliminating the micro fissures where oxidation is lodged. Unlike varnish, which is an external layer, polymerization creates a new hardened surface that fuses with the original structure of the plastic. Thermal shielding of the intake with aluminum. The air density is the key factor for power. Hot air is less dense, which means less oxygen for combustion. However, current engine compartments are ovens that heat the plastic intake pipes, raising the temperature of the air entering the engine to inefficient levels. The trick consists of applying a thermal shield using industrial-grade aluminum tape or ceramic insulators on all the piping that goes from the air filter to the throttle body. By wrapping these components, you create a reflective barrier that prevents the heat from the radiator and the engine block from preheating the intake air. In tests with real-time temperature sensors, this shielding can reduce the intake air temperature by up to 15 or 20 degrees Celsius. This translates into a real gain in engine torque and a better throttle response, especially in heavy traffic situations or extreme heat days. It is basic thermal engineering applied to obtain free performance. In the world of high-performance engineering, each reduction of 3 degrees Celsius in the intake air translates into a gain of 1% of net power. Factory plastic intakes act as thermal accumulators that preheat the air before it reaches the cylinders. The trick of shielding with aeronautical-grade aluminum tape works by reflecting up to 95% of the radiant heat from the engine. By wrapping the ducts, we ensure that the air maintains its maximum molecular density. In dynamometer tests, this insulation has been shown to reduce the intake temperature by more than 15 degrees in heavy traffic conditions, which is equivalent to recovering between 5 and 8 horsepower that were lost due to pure heat. Lubrication of engine mounts with industrial silicone. When the car vibrates at idle, the easy diagnosis of the mechanic is you have broken engine mounts. They all have to be changed. But many times the rubber is not broken, it has simply crystallized due to heat and age, becoming hard as a stone and transmitting all the engine pulsations to the chassis. The survival trick consists of deeply washing the mounts with degreaser and then saturating them with high-viscosity industrial silicone or dielectric silicone grease. Silicone has the property of penetrating the pores of old rubber, softening it and returning its elasticity. In cases of mounts that already have cracks, mechanics with limited resources inject high-density liquid polyurethane into the gaps of the original mount. Upon drying, this material creates a reinforced mount that is more durable than the original, and that eliminates vibrations immediately. You are saving an expensive part with applied chemistry in your own garage. Many diagnoses of unbalanced engine are actually mounts that have lost their damping coefficient. Natural rubber, under heat cycles of 100 degrees, suffers a process of secondary vulcanization that makes it rigid. The high-viscosity industrial silicone hack, 10,000 centistokes or more, allows the compound to penetrate the micro-cracks of the mount, acting as a rejuvenating agent that returns torsional flexibility. If the mount has empty cavities designed for comfort, the late piston ring seating procedure. This trick is the most radical on the list, and should only be done if your engine already consumes oil and has low compression. Many engines become oil wasters because they were driven too gently throughout their lives, which caused the piston rings to never expand correctly against the cylinder, creating a layer of hardened varnish known as glazing. The procedure consists of performing controlled aggressive driving. With the engine at working temperature, look for a road with climbs and accelerate to the floor in a short gear, second or third, from 2,000 to 5,500 revolutions, and then release the pedal completely, letting the engine brake the car down to 2,000 revolutions. Repeat this cycle 10 times. The pressure of the acceleration forces the rings to bite the cylinder wall and break the glazing, while the vacuum of the deceleration cleans the residues. It is surprising how engines that seemed condemned to a total reconstruction recover their power and stop burning oil after this shock treatment. This procedure is the last frontier before a $3,000 engine reconstruction. The glazing of the cylinders occurs when the piston rings never reached the optimal sealing pressure, creating a layer of vitrified varnish that allows the passage of oil. The trick consists of using a high-detergency mineral oil and subjecting the engine to controlled load cycles of load and vacuum. By accelerating to the floor on a slope and then releasing the pedal, letting the compression brake the vehicle, you generate a massive pressure differential. The WD-40 trick on ABS sensors. When the ABS system light comes on, most workshops want to change the wheel sensors, which are expensive parts. However, these sensors are magnetic and are exposed to moisture and metallic filings from the brake discs, which generates a layer of dirt that interrupts the signal. The trick consists of dismantling the sensor and cleaning both the tip of it and the toothed ring of the wheel with WD-40 or a quick drying contact cleaner. WD-40 is an excellent moisture displacer and helps to dissolve accumulated grease that traps metallic dust. By reinstalling the clean sensor and with a connector free of sulfation, the fault light usually disappears instantly. It is a $5 and 20-minute repair that manufacturers would prefer to replace with a $300 bill. The wheel speed sensors are in essence magnetic coils that read a toothed ring. The problem is that the metallic dust from the brake pads is highly ferromagnetic and stays stuck to the sensor, creating an electrical noise that confuses the ABS computer. The use of original WD-40, which is a moisture displacer and a mild solvent, is ideal because it does not attack the sensor insulation, but dissolves the grease that traps the filings. By cleaning both the tip of the sensor and the pulse ring, you restore the sharpness of the square wave signal that the computer needs. The low temperature thermostat modification. We reach the number one spot. Modern manufacturers design engines to work very hot, near 100 degrees Celsius, because at that temperature residues burn better and emissions are slightly reduced in laboratory tests. However, working so close to the boiling point prematurely degrades all the plastics, hoses and gaskets of the engine. The ultimate trick of high-performance mechanics is to modify the thermostat or install an early opening one that opens at 82 degrees instead of 95. By making the coolant circulate earlier, the engine block stays in a much more stable temperature zone, avoiding cylinder head deformations and the cooking of the oil seals. Although this may slightly increase fuel consumption by 1%, the gain in engine longevity is incalculable. It is the way to ensure that your car does not suffer a thermal death due to a design thought, only to comply with an emissions test and not to last 30 years on the street. The ultimate trick is a rebellion against planned obsolescence. Modern engines work at 98 or 105 degrees to reduce a minimal fraction of emissions, but that extreme heat cooks the valve seals, the head gaskets, and the plastics of the cooling system. Installing a thermostat that opens at 82 degrees radically changes the destiny of the engine. By reducing the operating temperature by 15 degrees, you double the useful life of all the rubber and plastic components of the engine bay. Furthermore, the oil maintains a more stable viscosity and does not oxidize as fast. You have reached the end of the forbidden knowledge. Now you have in your hands the intellectual tools to challenge the conventional maintenance system. These 20 tricks are not simple tips. They are a philosophy of mechanical resistance.